In 5.6 of Unit 5 for AP Chemistry, it is called the Reaction Energy Profile. It's another section where you may have some prior knowledge about the content that's in this section, and it could be better off covered at the beginning of the Unit 5. The terms, I'm not going to really define these terms. They are just going to be used on the graph. I'm just going to use like a shorthand or a symbol for it. And then I am going to cover the Arrhenius equation just a little bit, just because it is another way to find the rate constant. It will be your third way to find the rate constant for a reaction. First way was using a table, second was using the graphs, and then you could use the Arrhenius equation. Currently, right now, though, it's out of the scope of the AP curriculum. All right, so the first thing is that our reactants are going to be, I'm just going to use the letter R. And I'm not going to define what a reactant is in here. I'm just going to use these as examples for the graphs that are coming. P for products, and then activation energy, again, was the minimum amount of energy required for the collision to be effective if it has enough energy to break the bonds, and then also orientation. A new concept is actually called the activated complex. And the other thing I wanted to say about the activated complex is some people still use another term called a transition state. It's another version of the activated complex, like T or TS for transition state. I do believe activated complex is the most common one used. And then change in enthalpy from your, or for your future Unit 6, or if you've covered Unit 6 before this, or if you've had that in a past class. And then potential energy, we could use PE. And then the reaction coordinate doesn't really have a shorthand version. So down here, we're going to draw two graphs, one for endothermic and one for exothermic, or I should say energy profiles. So the first thing I'm going to have us do is like draw where does it start and where does it end and what are the axes. So for both of these, the axes are potential energy on the axes there, and then the bottom one is the reaction coordinate. I'm just going to do reaction and then coordinate like that. And same here. So it just means as time goes along, and the reaction proceeds. So it's kind of a blanket statement for just the reaction occurring. And so at the first one, what we'll do is we'll say, okay, well, maybe the reaction for an endothermic reaction, the reactants would start here at this potential energy. And then if it's endothermic, it has to go up to a higher energy as products. So again, your reactant would be here. So just put R. And your product will be here. And sometimes you can leave it as that, or just sometimes you'll see them. I'm not going to draw a line, but they'll just have a line that goes across like this, or they'll just have like where it starts and ends. But when we add in the concept of energy profiles, it has to actually go up to a higher energy and then come back down. And the definition of that is the activation energy. So that's our EA if you have to label these graphs. And then at the top of this graph is our activated complex, and I didn't really leave a lot of room for myself to write that, but at the top of this set here, I'll put it in black, is our activated complex at the peak of that. It's also the transition state. It's defined as where the particles are basically a reactant and a product at the same time almost, meaning they're in the midst of bonds breaking and bonds making. All right, the next thing that you'll end up having to label is the change in enthalpy. And for an endothermic reaction, this is key that you go from the reaction's energy to the product's energy. And that's our change in energy. And that would be a positive value in usually kilojoules per mole. So this is some positive number that you would have in kilojoules per mole. And that just means that energy is absorbed by the reaction. Instead of being released. And then the opposite will happen when you have an endothermic reaction. So for an endothermic reaction, you would say, okay, maybe my reactants start here. My products have to be down lower. And then if you connect it, it has to go up a little bit and then down. And the height of this amount is, again, our activation energy. There could be a large activation energy or a small activation energy. And again, the activated complex is at the top. You have reactants here, products here, and then if you label your enthalpy or your change in enthalpy, it's going to be from the reactant to the product. And so this one will have a negative enthalpy change. Negative just means that it is exothermic, and energy in the reaction is released overall after the reaction is done, per se, or at equilibrium even. And so this number would be a negative value, and then kilojoules per mole. Now, if the reaction were to go in reverse, that's something that does happen with these graphs, is if the reaction goes in the reverse direction, which if you talk about equilibrium, then the products have a lower energy, so then the reverse direction would be endothermic. And you'll see that if you flip these equations with what's called Hess's law, you just take this sign and you make it a positive. So if you run, again, this reaction reverse, it's like this. The other thing you might see is that what would the activation energy be for the reverse equation? It would be from here to here. So that would be the activation energy, but that again is for the reverse equation where you'd go this direction. So the reverse of an endothermic reaction, so if you go back to this one, the reverse of that one would be the activation energy would only be from here to here, and then you'd have if you ran it the opposite direction, products turning into reactants, then this value would be negative. And you might see that in some of the questions that you have to work through. All right, a really quick summary of the Arrhenius equation. So it is another way to find the rate constant. So K, again, just to review, I think it's good to just review these terms. So that's the rate constant. And you need to find that per that reaction, per a temperature. A is just going to be called the frequency factor. And I don't really want to get into it, but the frequency factor you'd find for that reaction, and it's got two other letters in it, but we don't really have to worry about that at this point. It has to do with the collisions and then the orientation. And then this is the activation energy. So what it's saying is if I know the activation energy, and I know the temperature, and then R, be careful, this is similar to the universal gas constant, but it's the 8.314 joules per Kelvin or Celsius, but per Kelvin per mole. I'm actually just going to line those up instead of doing a denominator thing like that. So per Kelvin, so -1, that's capital K, Kelvin, and then mole. So be careful with your letter K. It can stand for the equilibrium constant, or it can stand for the Kelvin temperature. And then the other powerful thing about this equation is, yes, you could solve for K. This is just the natural logarithmic scale E, so that's a math thing. This is a frequency factor you have to be given. Activation energy you'd be given, T and R. So you could find K, or sometimes if you know the rate constant, so let's say you know this side, you could find the activation energy of a reaction if you knew the A, the R, and the T. So the Arrhenius equation is not on the AP exam right now, but it is kind of a powerful equation for you to find some of these kinetic data variables for your reaction. All right, well, I hope that helped, and good luck with the 5.6 problems.